So there are many different ways to express solution concentration. We have two terms that are qualitative, dilute, and concentrated. And those mean the same thing that they mean in everyday life. So a dilute solution is going to have small quantities of solute relative to the amount of solvent. A concentrated solution is going to have large amounts of solute. And so those are relative terms. And then there's a whole bunch of quantitative measures. We've learned about a couple of them. We've learned about molarity. Molarity is moles of solute per volume of solution in liters, so moles per liter. Molality is the amount of solute in moles divided by the mass of the solvent in kilograms. That's a little different. Mole fraction, we've looked at that. That's the amount of solute in moles divided by the total amount of moles. So we talked about that when we talked about mixtures of gases. You can if you take the mole fraction and multiply by 100, you get a mole percent. And then we have parts by mass and parts by volume. So parts by mass would be the mass of the solute divided by the mass of the whole solution multiplied by a factor. And so you can have percent, which you multiply by 100. Right? There's 100 pennies in a dollar. You multiply by 100 to get percent. You can get parts per million, abbreviated ppm for parts per million. You multiply by a million. Parts per billion, it's the part over the whole times a billion, which is 10 to the 9. And so these are the units. You can also have parts by volume, these same different units, same different. Oh gosh. The same types of units, but there, instead of looking at the mass of solute and mass of solution, you're looking at volumes. And you can also have a mass to volume percent, parts per million, or parts per billion. Mass of solute per volume of solution. The reason we have all these different units is because they are useful in different situations. So molarity, we covered this in 4.4. This is how you would make a solution. You would weigh out the amount of solute, the moles that you need. If we're making a 1 molar solution of sodium chloride, we'd need 58.44 grams, the mass of 1 mole. We're going to put that in a volumetric flask and add water, the solvent. And we're not adding a liter of water. We want the total solution volume to be 1 liter. Because if you filled a glass to the very tippy top and then put in half a cup of salt, what would happen? The water would run over the sides, right? That's why we measure the volume of the solution instead of the volume of the solvent. And so you would fill this, get this to dissolve, fill it up to the line, which indicates this would be a 1 liter flask. And then you would mix it very well, and you'd have a 1 molar solution, 1 mole per liter. Molality is similar but different. So here we have amount of solute in moles, that's the same. But now we're doing the mass of solvent, not solution, solvent, in kilograms. The reason that this is useful at all is because it is independent of temperature. Molarity can change with temperature because when you heat a liquid, it expands, its volume changes. Molarity is dependent on the volume of the solution. So when you change the temperature, you can change the molarity. Most of the time, that doesn't matter, but sometimes it does. So here what we have is the mass of the solvent and the amount of solute in moles. Neither of those will change with temperature. This is not my favorite unit, molality. It's abbreviated with a lowercase italicized m. Like, that's not going to be confused with meters, right? People have enough trouble with the capital M for molarity. So this is, but we have to use it. So that's molality. So, yeah, if you see the word molality on an exam, occasionally I've had students think it was a typo and I meant molarity. I don't make typos like that. So if it's molality, it's molality. Spelling matters. Parts by mass, parts by volume. So this is just more details than were in that table earlier. Mass of solute divided by the mass of solution. The solution is the mass of the solvent and the mass of the solute. There will be a question on the exam over this material where I try to trick you. I'm telling you right now, I'm going to trick you. So, where I'll give you the mass of the solute and the mass of the solvent and ask you to find the mass percent. And the mistake a lot of people make is they divide mass of solute divided by mass of solvent, and they get the wrong answer because it's the mass of the solution. You have to add the two together for the denominator. We've used percent as a conversion factor before, and we'll need to do that again. Percent literally means per 100, parts per 100. And so when we see a percentage, 14% by mass, that means we have 14 grams of solute per 100 grams of solution. You can substitute any mass unit in there. You could have kilograms per 100 kilograms, milligrams per 100 milligrams. You could even do pounds per 100 pounds. It would come out the same. Parts per billion, parts per million. We can make these units into conversion factors as well. 15 parts per billion means 15 grams of solute per a billion grams of solution. That's going to be a very, very small amount, but this is useful for things like measuring contaminants in water. How much lead is in your drinking water? Well, it's going to be in the parts per billion range, but we want to measure it because if it gets above a certain level, then it causes problems. Parts per volume, same pattern, but now you're looking at the volume instead of the mass. Okay, so what mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. So this is a problem that you should be able to do, but it's not necessarily going to be immediately obvious to you. So you have to do some problem solving. So let's pull the numbers out and write them down and look at the units and see if we can figure out what to do. So the first number I've got there is 355 milliliters. Do you think we need the 12 ounces? No. That's just sort of for your own reference because you know what a 12-ounce can of soda looks like, right? 12 ounces is 355 milliliters. And then we've got 11.5 sucrose by mass. So 11.5% sucrose. What does 11.5% by mass mean? 11.5 grams of sucrose over what? 100 grams of water? The solution. Okay, and then we have a density, 1.04 grams per milliliter. So in that density, grams of what? Grams of the solution, right? The density would be grams of solution per milliliter of solution. Chemists get tired of writing the word solution, so we abbreviate it like that. And this 355 milliliters, is that 355 milliliters of sucrose or water? It's the solution, right? Okay, so we took those numbers and we labeled things, and we're trying to find mass of sucrose in grams. So let's think dimensional analysis. I'm trying to get grams of sucrose. And I have these three different things, and sometimes it's hard to know what should I start with. Should I start with the percent by mass? What do I start with? Well, look at the units here. Expanding percent, this is grams sucrose per 100 gram solution. That looks like it could be used as a conversion factor. And this looks like a conversion factor. Can I use 355 milliliters as a conversion factor? 355 milliliters of solution per what? Okay, it doesn't work as a conversion factor, right? So this is what I want to start with. So again, we're going to look for the unit that's simple, just a single unit. Here we have per units, this per that, this per that. Those are generally going to be conversion factors. So if I start with milliliters of solution, because that's what this unit is, I'm trying to get to grams of sucrose. Well, this term has grams of sucrose in it. This relates grams of sucrose to grams of solution. So if I had grams of solution, I could use that percentage to get to grams of sucrose. How do I get from milliliters of solution to grams of solution? The density. So there's no equation that you plug this stuff into. You look at the units. So we're starting out with 355 milliliters of solution. And we're going to grams of solution. So I'm going to put milliliters of solution down here. So I want those units to cancel out. And then I'm going to go to grams of sucrose and grams of solution. So those units cancel. The relationship between grams of solution and milliliters of solution is the density. So 1.04 grams of solution, so the 1.4 goes on top. And then this term, grams of sucrose and grams of solution, that's this guy right here. It's 11.5 grams of sucrose per 100 grams of solution. This is a relatively simple problem, and so some of you may be able to just push those numbers together and get it to come out. I would encourage you, though, to learn the process for figuring out the units, because there will be some other ones that are more complicated. So we need to calculate here 355 times 1.04 times 11.5 divided by 100. 42. How many sig figs? Looks like 3. 42.458. So that would round to 42.5 grams of sucrose. Any questions? Mole fraction and mole percent. Mole fraction is given the symbol chi. So chi solute would be the moles of solute divided by the total moles of the solution, the moles of solute and solvent. So it's a fraction. A fraction is a percentage that hasn't been multiplied by 100. So it's the part over the whole, but in moles. So we could also express it this way. Chi solute is the moles of solute divided by the sum of the moles of solute plus the moles of solvent. If you take that and multiply by 100, you get the mole percent. Okay, this is a fun one. Solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. So let's start at the top. Molarity. What's the definition of molarity? Moles per liter. Moles of sucrose per liter of solution. Well, do we have either of those? Not quite. We've got the solution in milliliters, right? So we could convert that to liters. So that's going to be 0.355 liters. But we're given a mass for the sucrose. 50.4 grams of sucrose, which is C12H22O11. How do we get moles out of that? Molar mass. So we got to calculate that. 12.01 times 12 plus 1.008 times 22 plus 11 times 16. 342.296. Do not round your molar masses to whole numbers. It's going to mess things up. It doesn't save that much time, and you get the wrong answer, and it's just not worth it. Keep extra digits until the very end. So 50.4 divided by the 342 is going to give me 0.147. We got starting with 3 sig figs, and then the next 2 digits are 24. And that's moles, right? Moles of sucrose. So I'm going to put that in the numerator here. 0.14724 moles. 0.14724 divided by 0.355. 0.41476. 3 sig figs. I'm going to write down 2 extras because I might want to use those. Use this in another calculation. Moles per liter, 0.415, capital M. Remember that the capital M means moles per liter. It does not mean moles. It doesn't mean meters. It's not mega. It's moles per liter. Okay, mole fraction. What's the mole fraction? Moles of what? The solute, so moles of sucrose. Divided by moles of what? The whole solution, right? So that's moles of sucrose plus the solvent, moles of water, right? So we calculated the moles of sucrose, so we can put that in there. 0.14724 moles. And then in the denominator, we've got that plus the moles of water. Well, we've got kilograms of water. So the decorative blue line is going to go away. So we can do a calculation there instead. So I've got 332 kilograms of water. How many grams is that? 332. So you can write that out if you're not comfortable with that. Kilo means 1,000. So we can convert to grams. And then to get moles of water, we're going to use the molar mass of water. 18.02 grams of water per mole. 0.332 divided by 18.02. 0.0184. 23. What did I do? I forgot the 1,000. How about 1.84? Okay, I'll don't do that. 1.8423 moles. Anybody else get that number? Wake up. Anybody else get the number? Anybody got their calculator out? Anybody?
Well, it's 332 divided by the molar mass, right?
Yeah.
Which is 18.
Mm-hmm.
How's it 1 point?
332 divided by 18.02. So I multiplied by 100 instead of 1,000 before. So yeah, I'm just really. This is why I need you to help me. That didn't seem right, but I wasn't. Okay, there we go. 18.423. That right? Okay, good. Phew. So that's what we're going to put down here. We have to add the moles of solute and solvent together. The unit down there is moles. Be careful when you do the calculation. 0.14724 divided by the quantity 0.14724 plus 18.423. I'm getting 0.0079288. This has 3 significant figures. This is actually going to be 3 significant figures also, and so this should be 3 significant figures. Remember, those leading zeros are not significant figures. Sometimes people round this to 0.008, thinking that they've got 3 sig figs. No. What's the units on mole fraction? No units, because it's moles over moles. They cancel out. So the answer, the correct answer here would be 0.00793 as the mole fraction. Which of these other concentrations would be very easy to do right now? The mole percent. The mole percent is the mole fraction times 100. So this equals mole fraction times, let's use a dot there instead, times 100. So we've got 0.0079288 times 100. Let's see if I can manage to do this one correct. 0.793%. I multiplied by 100 and I rounded in the same step. Okay, how about molality? Molality is what? Moles of sucrose divided by kilograms of water. It's always the solvent, yeah. It's moles of the solute divided by kilograms of the solvent.
What's the show like practicality ones?
Well, this is useful for things like colligative properties where you're looking at freezing point depression, boiling point elevation, because molality doesn't change with temperature. That's, as far as I know, the only good thing about it. Other than that, I think it's pretty stupid. But one thing that helps me remember that this is kilograms of water down here. A kilogram of water is 1,000 grams of water. Pure water is approximately 1 gram per milliliter. 1,000 milliliters is a liter. So this is comparable to a liter of water. So it's very close. So moles of sucrose, well, we've got that because we've been using that all over the place. 0.14724. And then we need kilograms of water. Oh, look, they gave that to us. 0.332 kilograms. 0.14724 divided by 0.332. So this is 0.44349. And rounding that would give us 0.443 lowercase m, italicized. 0.443 molal sucrose. Oh, I should probably put boxes around the others if I put a box around that. There's this one, there's that one, there's this one. And we need to find mass percent by mass. So that's going to be the mass of the solute, grams of sucrose, divided by the grams of the solution. So this is grams of sucrose plus grams of water. And it's a percent, so we multiply by 100. So we have grams of the sucrose, 50.4 grams. We're going to divide by that mass plus the mass of water in grams, which was 332 grams, times 100. The gram units here cancel out as well. 50.4 divided by the quantity of 50.4 plus 332 times 100, 13.179%, rounding to 3 sig figs, 13.2% sugar by mass. Any questions? Calculating one of these concentrations from an amount of solute and an amount of solvent is not too bad. What gets kind of confusing, and we had this on our lab where we were calculating the percent vinegar, is taking something like a percentage and figuring out what's the molality or what's the molarity from the percentage, or changing a percent by mass into a percent by volume. That can get trickier. So let's do one of those. What's the molarity of a 10.5% by mass glucose solution? We need the density. Density is 1.03 grams per milliliter. Okay, so let's write down the numbers. We have 10.5% glucose. And percent means parts per 100 parts. So that is 10.5 grams of glucose per 100 grams of solution. And then we have density, 1.03 grams per milliliter. And that's the density of the solution, so it's grams of solution per milliliter of solution. So we're asked to find molarity, moles of glucose per liter of solution. And we look at the numbers that we're given, and they both look like conversion factors, don't they? Well, there's a couple of different things that we can do here. The more sophisticated thing is to say, well, this is a concentration unit, I'm going to start with this, and I'm going to convert the top and the bottom as needed to get to this. Students who can do that usually don't need much help doing it, so I'm not going to go over that. The other way is to break it into two pieces, which gives you less dealing with fractions, which tends to be more successful for more students. So what we need is we need moles of glucose and we need liters of solution. So a concentration does not depend on how much stuff you have. If you have a liter, if you have 1,000,000 liters, the concentration is the same. That's why there's no volume or anything given here, because it's not needed. But if we want to calculate how many moles of glucose or how many liters of solution, then we need something to start with, right? So we can choose something easy. What if we say, well, let's say we have a liter of this solution. So just choose to use 1 liter. Choose 1 liter of solution. Oh, I started writing the whole word. I have to write the whole word. So if I do that, what's in my denominator? 1 liter of solution. So what do I need to calculate then? I need to calculate the moles of glucose in 1 liter of solution. So 1 liter of solution, and I'm trying to get to moles of glucose. Well, I need to get from solution liters here, I need to get to grams, because I've got grams in here, right? Maybe we should write the path up at the top. I'm starting with 1 liter of solution, and I'm trying to calculate moles of glucose. I could go from liters to milliliters, and then I can go to grams of solution. Okay, that's not going to work. Grams of glucose, and then moles of glucose. Liters to milliliters, that's a metric conversion. Milliliters of solution to grams of solution, that's using the density. Grams of solution to grams of glucose, that's the percent by mass. And then I'm going to use the molar mass to convert to moles. So I've got 1 milliliter up here. I'm going to have 10 to the minus third liters down there. And then I'm going to use the 1.03 grams of solution per milliliter of solution. And then I want to get to grams of glucose. So I'm going to have 10.5 grams of glucose per 100 grams of solution. That's from this mass percent. And then I need to get to moles of glucose. There are grams of glucose down there. I need the molar mass of glucose, which I can never quite remember. Not well enough. 6 times 12.01 plus 12 times 1.008 plus 6 times 16, 180.156. That sounds right. So I've got 1 liter divided by 10 to the minus 3 times 1.03 times 10.5 divided by 100 and divided by 180.156. Getting 0.600313. 3 significant figures, and so that's going to round to 0.600 molar. Well, wait. Jumping ahead. We were calculating moles there, right? Moles of glucose. My molarity is moles of glucose per liter of solution. So I just calculated moles of glucose. And I'm going to divide by the volume I chose to use, which is 1 liter. And so I end up with 0.600 moles per liter. 0.600 capital M. Any questions? Yeah.
Would it have worked the same if you would have chosen the
Yeah, if you chose 2 liters or 7.938 liters, it'd come out the same. It might be a little more work, right? Because you got to divide by, you got different numbers to start with. Choosing one of something is always the easiest. Choosing 1 mole or 1 liter is easy. Any questions? If you can't write this out and you're just trying to do it by thinking about it, very easy to screw up. So if you haven't learned how to write units down like this, it's not too late. Yes?
I did it the other way where you just convert the 10.5 to molarity. I got 6.00 times 10 to the 8.
Did you convert milliliters to liters?